Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to finally start talking about molecules, and we're going to do so by building up Lewis dot structures, which can be used to make line structures to represent the where the electrons are in a molecular species. So one of the reasons why it's very important to build up these molecular structures is because molecular formula often isn't enough. So when we're taking a look at species, for example, we have here on the right, we have glucose. Now, glucose has a very common sort of molecular formula, C6H12O6. And it turns out there's a whole bunch of different sugars that you can make all with that same formula. You can make fructose, glucose, galactose. Plenty of non-digestible sugars, but only this specific one is used by the body so ubiquitously. And it turns out that if you switch the position of one of these alcohols, you can render the whole thing undigestible. So we need to make sure we know exactly what our molecular structures are. And we have very similar things with things like stearic acid, which is found in most soaps. And it's a fat that I can readily digest. You change the structure just a little bit, and it's not quite so usable by your body. So we're going to want to make sure we're very specific about the exact arrangements that these atoms that form a molecule, because that can really change things like the reactivity. It can also, like fats, change the solubility. You rearrange the species, it may be a liquid instead of a solid. It may not dissolve in water, or it may. And so we need to be very clear about these properties. And we're going to try and use our understanding of electrons to help predict structure. And then we'll use this to help talk about reactivity and other properties. So all of these essentially go down to this basic property of how much each atom wants electrons. So to a certain extent, it's all about electron configuration and electronegativity. So one of the easiest ways we can build up these molecular structures is by starting with this idea that atomic interactions are determined by the valence electrons. So this helps build up Lewis theory, which starts with the idea of I write an element and I put a single dot around it for each valence electron. So for example, if I've got hydrogen, it only has one electron. However, if I have something like lithium, it also only has one valence electron because we're going to ignore those two core electrons in the 1s shell. Carbon is going to have 4 valence electrons. Nitrogen has 5, oxygen 6, and chlorine 7. However, it turns out that most of these atoms are going to be the happiest with a full orbital shell. So for most of our main group elements, this means they all want 8 electrons. So for lithium, it's going to typically try and get rid of an electron to generate a full shell because we have those full core electron shells, in this case 2. Hydrogen can gain 1 electron and have a full shell, or can lose an electron and have a full shell. But most of the time, we're going to be looking at things like carbon, nitrogen, oxygen, chlorine, fluorine, sulfur. All of these elements want to have 8 electrons to generate their full shell. And as such, we tend to talk about full octets because all of these elements are going to be the most happy if they have 8 electrons either in their shell or are shared in their shell. So they spend enough time near the atom to at least make the atom think it has a full shell. So in order to do this, we can go ahead and take a look at a modified form of the periodic table, looking at the Lewis structure for each element. And you're going to find that, not too surprisingly, the valence electrons are really determined by what group the atom belongs in. So for example, all group 3 elements will have 3 valence electrons, group 4, 4, 5, 5, and so on and so forth. With the notable exception of helium and hydrogen, because they can only have 2 electrons in their valence shell before we move on to lithium. And for the most part, we're going to ignore our metals for now, as this octet rule tends to hold for these main group elements. So in order to generate our full valence shell, electrons can essentially either be shared or they can be stolen. So the simplest case is if one atom literally just steals somebody else's electrons. And this helps form ionic compounds. So if I've got an ionic compound, they're formed by a highly electronegative element and a very weak, electronegatively weak element. So think about something like lithium or sodium and chlorine or fluorine. So chlorine really wants an electron, so it goes ahead and it mugs the electron from lithium. Lithium now has its full shell, it's pretty happy. Chlorine has its full shell, it's pretty happy. Unfortunately, lithium now has a positive charge, chlorine has a negative charge. So what ends up happening is that these two atoms are going to be held together by Coulombic attractions, because positives like negatives and negatives like positives. So they stay pretty close to each other unless I surround them by something like water. And you can actually apply this to more complicated systems like calcium and chlorine. Chlorine wants electrons, calcium not so much. However, each chlorine only wants one electron, and calcium has two. So two chlorines gang up, they mug the calcium. Calcium loses both of its electrons. Chlorine has them, and then calcium essentially follows the chlorines around to help keep the whole complex charge neutral. And this is how we get things like ionic solids, because after these electrons are transferred, everybody tries to hang together to keep the whole system neutral. However, things get a lot more interesting when electrons are shared between two atoms. So these tend to happen when elements have similar electronegativities, or at least close enough, like chlorine and hydrogen. So chlorine wants that electron way more than hydrogen. So what ends up happening is it says, hey, hydrogen, give me the electron. Hydrogen says, sure, but I want an electron in exchange. So they end up sharing these two electrons in a valence shell. So when we're looking at valence shells, any electrons that are shared are essentially considered part of the adjoining atom's valence shell. So in this case, chlorine has 8 electrons and hydrogen has 2. However, due to electronegativity, that chlorine will have the electrons a little bit more often than helium has its 2. And to represent the formation of these shared electrons are called a bond, and we draw these with a straight arrow. However, if it helps you, go ahead and put a dot at each end of this line to help represent the 2 electrons that are present there. And this way, chlorine has its octet and hydrogen has its quote unquote octet. However, the strength of the bond can be represented by bond order, which is essentially the number of half the number of shared electrons. So let's take a look at a more complex system. Nitrogen has 5 electrons. However, 2 nitrogen atoms, each with 5 electrons, they both want 8. And the way they can make this happen is this nitrogen says, okay, if I give you 3 electrons, you'll give me 3 electrons. So these 3 electrons pair up, giving us 6 total shared electrons, or 3 bonds. And so we have a bond order of 3, making a fairly tight complex in between my 2 nitrogen atoms. However, again, when we're looking at the number of shared electrons, this nitrogen, when we count the bonded electrons, has 8. This nitrogen has 8, giving us both of these atoms satisfy their octet rule, even if, unlike these, what we call lone pair electrons, they may not have all of these electrons all of the time. They have all of these electrons most of the time, which is good enough. And that's really kind of what makes these covalent bonds. So next time, we're going to be trying to examine how you can build your own Lewis structures for systems that are a little bit more complicated than simple diatomics. Until then, take care.